Well, hello there, good people. Today we are talking about nuclear fusion. Now, when we talk nuclear fusion is really the second part of a two-part lesson on nuclear fission and nuclear fusion. When we talk nuclear fusion, we're going to see a lot of similarities to what we talked about with nuclear fission. And where we're going to start is the same place we started with nuclear fission, with this graph. Go ahead and take a look. Wait for it. Wait for it. Wait for it, yeah. Any Hamilton people out there? Okay, cool. Well, anyway. There it is. Okay, here on the y-axis we have mass per nucleon. Here on the x-axis we have atomic number. Now, here's what we saw with nuclear fission. Is we said, what if we could split, and I'll move this up here. We said, what if we could split a uranium-235 nucleus into barium and krypton? Well, if we split it, then the nucleus would get more stable. And getting more stable, it would increase its binding energy. And if its binding energy is increasing, then its protons and its neutrons would get smaller. And if the mass per nucleon decreased, decreasing the mass per nucleon would release mass in the form of energy. And so ultimately, you could release a lot of energy by splitting a uranium-235 nucleus into these smaller nuclei that have a higher binding energy and smaller protons and neutrons. If you can shrink the protons and neutrons, you can get a whole lot of energy. That's this half of the graph. Today, we're talking the other half of the graph. Check this out. Here we have hydrogen. Hydrogen has pretty big nuclei, or pretty big protons and neutrons, big nucleons, because it has very low binding energy. If binding energy is how hard it is to rip apart a nucleus, well, it's not very hard to rip apart a hydrogen nucleus because it's only two little guys right in there. So, at least with this particular isotope with H2. With H2, you pull apart a hydrogen and a neutron. Whoa, let me try again. You pull apart a proton and a neutron, and that's the whole thing. That's the whole shebang. And so, that thing does not have very much binding energy. And since it has such low binding energy, the mass of the protons and the neutrons is relatively large. The protons and neutrons are pretty big. But as you combine those protons and neutrons with other stuff, you get a nucleus like a helium-4 nucleus. A helium-4 nucleus is slightly bigger, and so it has a slightly higher binding energy because it's a little bit harder to rip apart. That means the protons and neutrons are slightly smaller in helium than they are in hydrogen. You remember this from yesterday, that as you go towards iron, either on this side or on this side, the protons and neutrons get smaller, and they're the smallest in iron. The idea is if we can shrink the protons and neutrons, we can release a whole lot of energy. If we're shrinking these protons and neutrons by splitting the uranium, we get energy. Or we could also shrink the protons and neutrons by combining them into a new nucleus. If we combine them into a new nucleus, then the protons and neutrons will get smaller and you'll release a whole lot of energy. That's the idea of nuclear fusion. Check it out. Suppose, let me go ahead and escape from this thing. Set me free. Wait, hang on. Okay, come on. Here we go. And back over here. Okay, perfect. Suppose that we were looking at a nuclear fusion reaction. Here's the kind of reaction that would be a nuclear fusion reaction. Suppose that we took a hydrogen and another hydrogen. This particular isotope of hydrogen is an isotope that we call deuterium. We call it deuterium because it has one proton and one neutron, which means it has an atomic mass of 2. And so we call it a deuterium because deut means 2. So we have 2 deuteriums right here, 2 little isotopes of hydrogen. If you smush them together, then you can make a little helium. Hey, here's a question for you. Where's all the mass of the sun going? The mass The sun is losing about 1,000,000 elephants per second worth of mass. That is a lot of mass. Where is it all coming from? From nuclear fusion. What's the sun made of? Hydrogen, becoming helium. The sun is made up of mostly hydrogen, and that hydrogen is gradually becoming helium through the process of nuclear fusion. In the center of the sun, two hydrogens will get slammed together, and then they'll turn into helium. And when they get slammed together, their protons and neutrons shrink. And so the mass that's leaving the sun is the mass of all of the protons and neutrons that are shrinking as they get smaller as they become helium. Let's see exactly how much energy this kind of reaction would release. First, you need to know a few things. You would need to know the mass of a deuterium, this particular isotope of hydrogen. You would also probably want to know the mass of helium. Not just any old helium, probably a helium-4 would be the most useful to you. And finally, we're looking for the amount of energy that gets released in this nuclear fusion. Let's check it out. The mass of a deuterium, of a little hydrogen, is going to be 2.014102 atomic mass units. The mass of a helium is going to be something like 4.002602 atomic mass units. And that's pretty much everything we need. The first thing that we do is always the same. We find the mass defect between what we had before and what we have at the end. We know that the mass defect is always, for these kinds of problems, going to equal the mass of the reactants minus the mass of the products. Because the reactants will always have more mass than the products do. That's why we do nuclear fusion in the first place, is to get rid of mass in the form of energy. Our reactants here, we got 2. So because they're the same, I'm gonna write it as 2 times the mass of a little, not that yet. Whoop, boop, boop. Okay, sorry. 2 times the mass of our little deuterium here, of our little hydrogen. That's the mass of my reactants. The mass of my products is going to be the mass of one little helium. So the mass of one little helium here, we'll write it as M with a little 4, 2, and a little helium, just like so. Now we can plug in numbers to find the mass defect. When I plug in numbers, I get 2 times, and here's my number, 2.01412 atomic mass units. And then on my product side, I got 4.002602 atomic mass units. Plug that into your calculator, and you get something like 0.025602 atomic mass units. But are we done? No. You say we still got a lot of work to get to delta E, the change in energy or the energy that's released. First, don't I have to convert this into kilograms? For sure. If I want to know the mass in kilograms, I got to take the mass in atomic mass units and do a little unit conversion with it. So I take the mass that I already have. In my unit conversion, I know that 1 atomic mass unit is equal to 1.6605 times 10 to the negative 27th kilograms. And that's the mass of one little proton in carbon, you'll remember. Plug that into your calculator, and you get a number like 4.2512 times 10 to the, that's a 4.2512, sorry, times 10 to the negative 29th kilograms. But we are not yet done. Now that we have the mass in kilograms, now we need to find the amount of energy that's released. To do that, we use delta E equals delta mc squared. So we start here. Delta E is equal to delta m times c squared. Delta m, we just found this on the last page. It's 4.2512 times 10 to the negative 29th kilograms. C is, as we know, 299792458 meters per second. Square that whole thing, type it into your calculator, and you would get something like 3.8207989 times 10 to the negative 12 joules. Notice that I'm leaving a ton of extra sig figs here so that I'm plugging in unrounded values. Then, take that, we're not done. We got to find the difference in energy, the amount of energy that was released in mega electron volts. To do this, we're going to take the special number 3.820799 times 10 to the negative 12 joules. That's the number that we just found. And we're going to get it into electron volts. To do that, we're going to go from joules to electron volts. Now, you all know that in 1 electron volt, you get 1.602 times 10 to the negative 19th joules. Now, to get that into mega electron volts, on top, get rid of our electron volts on the bottom. To get into mega electron volts, we know that 1 mega electron volt is worth 1 times 10 to the 6th electron volts. Type that into your calculator and you get a number like 23.85 mega electron volts. And that's it, ladies and gents. This is the amount of energy that is released when you take 2 deuteriums and combine them to make a helium. Now, if you'll remember from nuclear fission from our last video, you'll remember that from the nuclear fission of 1 uranium into krypton and barium, it was worth 173.5 mega electron volts, if I remember that correctly. So a lot of students will look at this and they'll say, fission is more powerful than fusion. But that's not true. Remember that uranium is way bigger of an atom than hydrogen is. If we wanted to look at the amount of energy that's released per nucleon, like how much energy is released for every proton and neutron that you're talking about here, the amount of energy that's released per nucleon we'll start here. For this guy is equal to, we just take this divided by 235, is equal to, actually 236, because we have that one extra neutron that comes in. But anyway, the amount of energy that's released per nucleon is equal to 0.7338-ish mega electron volts per nucleon. That says nucleon, by the way. This one, the one that we just did today, this amount of energy per nucleon is 5.9625 mega electron volts per nucleon. Here's what that means. Per nucleon, fusion is way more energy than fission. This means that if you did let's say that you did nuclear fusion with a gram of hydrogen versus with a gram of uranium, where are you getting a lot more energy? Fusing that hydrogen. We can see that if you look back at this graph over here. Check it out. Wait. Oh, it's got to load again. Loading. Unadulterated loading. This is, I guess this is just musical time here. This is my most musical-y video that you're ever going to get. Okay, here we go. Notice this section of the graph is way steeper here than this section of the graph, which means that the mass of the protons and neutrons is changing more dramatically for nuclear fusion than it is for nuclear fission. If you notice here, you're going to get a huge change in the mass of the protons and the neutrons. Here you're going to get a slighter change if you look on just our y-axis in the mass of the protons and the neutrons. Which means that this, if it's releasing more mass or you're losing more mass, that also means that you are gaining more energy or you're releasing more energy out into the world. If these protons and neutrons are releasing more mass, they're releasing more energy. That's the idea. So fusion gives you way more energy than fission does. Back over here. Okay. Back over here. You'll also notice if you looked at our nuclear fusion reaction, check out the products and the reactants here. Your product is helium. Helium is not radioactive, and it's not even a greenhouse gas. It is totally perfectly safe for the environment. And your fuel is hydrogen. Hydrogen is quite abundant. Unlike uranium-235, which is really hard to find, hydrogen is, well, everywhere. If you went to the ocean, for example, the water in the ocean is made up of H2O. You got 2 little hydrogens right there for every little water molecule in the ocean. So nuclear fusion is awesome for a lot of reasons. First, it doesn't create any bad products, and also the reactants are like in abundance everywhere. It's so easy to find hydrogen. This is the part in the lesson where students normally start to say, oh, okay, Miss Wilson, wait a second. You're saying that we can get way more energy with no bad products, like no nuclear waste, and also the fuel that we need for this reaction is literally everywhere and is easy to find. Why are we not doing nuclear fusion all the time? Well, here's why. Nuclear fusion, if you look at this little equation, nuclear fusion involves putting together a hydrogen nucleus and a hydrogen nucleus. What charge does a hydrogen nucleus have? You say positive. What charge does another hydrogen nucleus have? You say definitely still positive. Hey, if you take a positive charge and a positive charge and you say, okay, friends, be buddies, how much are they going to like being squished together? Not at all. They would much rather avoid each other. If you take a little hydrogen nucleus and a little hydrogen nucleus and you say, okay, guys, now be friends, and you try to shove them towards each other, they'll go and run back the other direction. The electromagnetic force will shove them apart. So in order to get them to stick, because they won't stick until they touch, that's how the nuclear strong force works. The nuclear strong force is like glue. You got to be touching each other for it to stick. And by touching each other, I mean within times 10 to the negative 15th meters apart. You have to be so super close. If we want the nuclear strong force to work, then we have to get them shoved at each other at really, really high speeds. Which means we got to get this up to a very, very high temperature. Now, I'm not talking like warm, sunny day in the summer kind of high temperature. I'm talking like 350 million degrees Celsius. For the sun, 350 million degrees Celsius is not that big of an issue. But for us on Earth, if I say, hey, could you just heat up that thing to 350 million degrees Celsius? You'd say, Miss Wilson, you're a crazy person. No, that's nearly impossible. It takes so much energy to get to 350 million degrees Celsius. Then, if we could get all the hydrogen to be 350 million degrees Celsius, what container are we going to hold our hydrogen in? Because we need a container that can withstand 350 million degrees Celsius without melting. Tough stuff. So what we've tried so far is we can't use a normal container to hold our hydrogen at 350 million degrees Celsius. What we use instead is we use magnetic and electric fields, because electric fields and magnetic fields can't melt. So here are some of our strategies. I'll show you over here. Let's pull up a new little tab here. Yeah. Incoming tab. Here it comes. Okay, let's try blue. Okay, here's one strategy that we try. One strategy is to take 2 plates like this and another 2 plates like this. We give, I want a little more space here. Okay. We give one of these plates a super positive charge like this. We give the opposing plate a super negative charge like this. Same thing on this side. We give this plate a super positive charge like this. And we give the opposing plate a super negative charge like this. And then what we do is we take our little hydrogen nuclei. Here is one. And over here is another little guy. We take our little hydrogen nuclei, which are repelled by the positives and pulled towards the negatives. This puts them in a little electric field between the plates. And then the electric field will shove these two little guys together, and when they meet in the middle, they shall fuse, and they shall create a little helium. Now, this strategy definitely works. We get it heated up nice and hot, then we use our little electric field to shove them together, but here's the problem. The amount of energy that it takes to get them up to this temperature and to get them going that fast enough to really, truly collide with each other in order to create an electric field that's strong. The amount of energy that takes is more than the amount of energy that's actually released in the reaction. So we can do it, but it's just not very, energy efficient. So here's what some people said. Some people said, okay, we're wasting too much energy creating this electric field here. What if we did something else? What if we instead created a little magnetic field like this? So we'll start with the same idea. We'll start with a little electric field here and a little electric field here. And they said, same idea as last time. Let's put some positive charge on this side. We'll put some negative charge on this side. We'll put some negative charge over here on this little plate, and we'll put some positive charge over here on this little plate. And then they said, let's get our little hydrogen atoms ready for launch. So you put a little hydrogen nucleus over there, you take a little hydrogen nucleus and you put it over here, and then you launch them. Or I should say, they launch themselves, because they do not like those positives and they do like the negatives, so they go this way and this way. Then, in between these plates, you put a little magnetic field, like this. Oh, sorry for my uneven drawing here. It just is what it is. You put a little magnetic field like this. And here's what happens. Use your right-hand rule. The charge on the bottom is going to the right. You point your fingers into the board or into the screen, and your palm is pushing up. So our little guy on the bottom here is going to go upwards, like this. Meanwhile, our little guy on the top is going this way. Magnetic field is going in, so he's going to get shoved down and going to meet up with the other guy like this. And they'll both end up meeting at the same place. Now, people thought this was a very effective strategy because they said it's going to take us less energy in the electric field here. It's mostly just going to be in the magnetic field. But then it turns out that the magnetic field still required a lot of energy. And so at the end of the day, it still required more energy to make this happen than it actually released in the nuclear fusion. Now, this put us in quite a pickle. It turns out that actually we have had some nuclear reactors that can do nuclear fusion, and they can get it up to a temperature of 350 million degrees Celsius. However, we've only been able to sustain a reactor like that for about 23 minutes before all of it kind of falls apart. So that is not like a super great option for us because it doesn't really work long term. You could imagine how it would be a really cool 23 minutes, but after that, it's not powering the city anymore. So this is really where we're at right now because we don't have a good solution for this. So maybe you could be the person to find the solution for this. And when you do find the solution for this, please let me know because I really want to know what your strategies are like. But that we're running into a bunch of engineering difficulties to make this work. But you should know that if we could make this work, it would be so crazy beneficial and efficient for creating energy for our society and for our cities. It turns out that fusion releases about 4 times as much energy as fission. And also, the byproducts, whoa, sorry, I got totally distracted in my brain. Don't worry, I'm totally back with you. It creates about 4 times as much energy as fission, and the byproducts are totally safe and not radioactive. And the fuel for it is the most plentiful element in the universe. So this would make it really helpful. If you took 30 liters of seawater, you could get from those 30 liters of seawater 1 gram of deuterium, 1 gram of hydrogen-2. And that 1 gram of hydrogen-2 could create as much energy through nuclear fusion. It could release as much energy as 80 tons of TNT. That's enough energy to power a house for 40 years. So, as things currently stand, we don't have a good way of harnessing that potential, but we know that that potential is out there, and that is hopefully something that we can advance in the future. So that's a little bit on nuclear fusion. If you want to try some practice problems, I have 2 practice problems that you could try. Let me tell you what they are. The first practice problem that you could try is a nuclear fission problem. So this is something more related to what we did yesterday. Here's a nuclear fission problem that you could do. Try this. If you had, actually I'm going to move this down a little bit. Bye. Okay. If you had a neutron and you threw a neutron as hard as you possibly could at a uranium-235, and that uranium-235 then splits. When we looked at a problem last time, we saw that it splits into krypton and barium, but that's not always true. It can split into other things depending on where it splits. One possible reaction looks kind of something like this. Get a little xenon going up in here. Here's a practice problem that you could try. First, can you figure out what is missing in this equation? We're missing one last thing, and what is it? Second, could you find out how much energy this thing releases? That's your first practice problem. Here's your second practice problem. Today in class, we looked at two deuteriums that combine together to make helium, but that's not the only possibility for fusion. Sometimes you get other isotopes of hydrogen, something like this, for example. This is what we call a tritium, and it is a hydrogen that has one proton and two neutrons. And these two can combine to make a helium and something else. Can you find out what that something else is? And then can you also figure out how much energy would be released by this reaction? Those are your two practice problems that you could try today. I hope you have a wonderful rest of your day, and I will see you all next time. Bye, good people.